I think we're going to do something that we've never done before. I like new things.
All right, welcome everybody to the latest Hashing It Out episode with Leo. He's a member of the Codex team and also a very prolific PhD researcher. He's worked with the EF in the past on various different grants, and yeah, he's here with us to talk about data availability sampling. I'll hand it off to you, Leo.
Hi, thank you for the introduction. Nice to be here.
Good deal. So, I mean, we're talking about data availability sampling. The obvious question is, what is sampling? And then the follow up immediately to that is, when do we need it?
Right. So, in the context of decentralized system, which is I think what we are talking here, in the context of Codex and Web3 and peer-to-peer networks, and so on and so forth, we need to be aware that not all the players in the network are first good players, and also there are other players in the system that even if they had good intentions, they might not achieve or with what the objective that they are supposed to achieve, or provide the performance that they're expected to provide to the network. So because of that, it's necessary to guarantee that a certain number of items or rules, depending on what is that you are designing, and for that sometimes you will need sampling. For example, if you are developing a decentralized storage system, and the nodes that are going to store the data in this decentralized system are just random nodes that can join at any moment at any time, you need to make sure that they are behaving properly, and that they actually are storing the data that they are supposed to store. And the best way to do that is sampling. So that means you're going to go to ask them what the data that they are supposed to have. And there are many ways of doing that, but I'm not going to get there yet. But yeah, basically you need to make sure that the data that they are supposed to store, they have it, and that everything is fine. And so there will be some nodes that are not malicious, but they're for X reason they go offline from time to time, either because of network conditions, bad internet, hardware failures, or many other attacks. And so perhaps at that moment they will not be available for relaying the data they are supposed to have. And there are other nodes that are just really malicious, and they are just trying to attack the system. So those are the things that you have to take into account, and that's why you need sampling.
Nice. So, if I were like a student in your classroom, my follow up is just I'm a seek for understanding. You do the data sampling to make sure that the data is there, right?
Mm-hmm.
So that's it. If I could distill it down, we've got to take samples of different nodes and what data they have to see if we have the complete set of data we need.
Mm-hmm. Exactly. So, for example, you take a data set and you want to distribute it among a group of people.
Mm-hmm.
And then, so you take your, let's imagine it's a book, right? And it has 20 chapters, and you're going to divide it into 20 people. So what you do is you just give a chapter for each person, and then from time to time you ask a certain person, can you give me, a proof that you still have the chapter that you are supposed to have, right? And then that proof, can be many ways. One of the ways is to, show me the chapter. So I just show it to you, like, hey, here it is, and that's a way to do it. Now there are other ways. For example, you could imagine, instead of sending you the whole data, the whole chapter through the internet, because maybe it's too heavy, you can do maybe just a hash of it. A hash is like a cryptographic signature, and then you send me the hash, and I know that that's the hash of that chapter. And so I say, okay, yeah, he still has the hash, right? And I assume that that everything goes well, and so that means you still have the data. Now, a hash is not really a good proof because you could take the chapter, calculate the hash, and then discard the chapter, right? And then you just store the hash. And so a hash per se is not a really good proof, but there are many other type of proofs. And sampling is just a way of analyzing, you know, statistically how many people should I check in a system where with a certain number of assumptions, and to make sure that I have the data, that I will recover the data that I'm supposed to have.
Okay, I'm tracking. I can keep rattling off questions left and right, Jesse, like a machine gun. But if you want to hop in, you gotta let me know.
So to solve the sampling issue of like sampling the entire chapter of the book that you're referencing, you mentioned sampling hashes or sampling like some sort of cryptographic proof that they have a fraction of the chapter maybe. So can you
Right.
go a little bit into how that chapter is specifically turned into maybe smaller subchapters or
Right.
like using some sort of maybe encoding scheme?
Right. So um, so sampling is one part of asking, the set of players in your network whether they still have the data that they are supposed to have or not. But then what happens when one of them don't, like, one of them just disappear, and it turns out that now that you cannot read the book because there is a chapter missing, right? So what we do, in computer science, and is to use different techniques for enhancing the data, or like augmenting the data, so that even if a few players, a few members of this group, or a few nodes in the network disappear, you still can't recover the data, right? The most simple way to do that is just replicating the data. Like, you just double the number of, you duplicate each chapter, and then you give one chapter to each person. But now if you have 20 chapters, you don't need 20 people, you need 40 people, because you need, you will not give two times the same chapter to that person, because then if that person disappeared, then you still lose the chapter. So you need more people, okay? And then if you want to tolerate multiple people missing, then you will have to replicate more times. So you can replicate it 3 times, 4 times, 5 times. Now, this is extremely simple, fast, and not complex, so it's easy to implement. The problem is that it's very, space hungry. It takes a lot of space, right? It requires a lot of storage. And if you really want to tolerate multiple failures or multiple missing chapters, then you will require a lot of storage and a lot of people helping you in this protocol. So instead of that, there's another system that we use that is called erasure coding. It's just a fancy term to refer to polynomials and mathematical equations and systems of multiple equations that help us solve us when something is not known in this system. But I think there will be another podcast in the future, maybe, that I'll explain more in detail how erasure codes goes, and perhaps we can leave those details for later. But it's basically, just imagine that you have a machine, right, in which you give it data as input, and then on the other side you get the data plus some extra data, right? And what happens is that with this extra data that you get, you can recover a certain number of pieces in the original data, right? And this is used everywhere today. Like if you want to communicate with satellites, you need that, right? Because when you are communicating with satellites, you have to pass through the atmosphere, and in the atmosphere there is a lot of perturbations and noise. And so you might lose small parts of the message that you are sending. So if you just send a message, you will never get,
Mm.
you will never be able to communicate with satellites, which is annoying because then we don't have GPS and then we don't know where we are going with driving. And then that's why we need to improve this message with this some kind of encoded data, so that even if some parts of the message are missing, we are able to reconstruct them with this mathematical magical box that allow us to encode and decode the messages, right? And so that's what we do. We take this data, we encode it, we produce some extra data, and then we divide all this in little boxes or blocks, and then we give to each node in the network a different block. So imagine you have this same chapter, same book with 20 chapters. You divide it into 20 chapters. You get all the chapters to this magical mathematical machine, and then you get 10 extra chapters that don't look like anything. They are just not readable. But it doesn't matter. The thing is that if you lose one of those chapters, you will be able to reconstruct it based on the encoded data that you got. And so now you don't need 20 people, but you need 30, because you have 20 original plus 10 encoded chapters. And so you disperse these chapters into 30 people, but now you can tolerate any 10 chapters missing in the entire set. Okay. And you only need 10 more people. If you wanted to do the same with replication, you would basically need to multiply the number of chapters by 10. So 20 times 10, that means 200. You will need 200 people to do that. In this case, we just need 30. It's much more efficient in terms of space. And then now you have a system that is much more reliable, in that is much, much harder to lose data. And then you apply sampling. Now you need to ask people from time to time, hey, you still have your chapter. But the question here is, do you need to really question everyone or not? Or is it sufficient to question only a few members of the group, whether they have their data or not? And the answer is, we don't need to ask everyone. And that's what we call sublinear sampling. It's like, if you apply some statistical computations, you can be sure that, or you can have a very high probability that you will still be able to recover that data if you got a sufficient number of positive answers when you are doing sampling. I don't know if does this make sense?
No, it actually does. I'm a little bit like kind of fascinated a little bit because I've asked, and I feel like you've explained it in a way that I finally can understand. So let me try to run it back. So essentially, what erasure coding does is it just provides some like redundancy in the message. So
Mhm.
like, okay, I'm sending a recipe, but I want to make sure everyone who downloads this recipe is going to get all the ingredients. So some of these ingredients I'm going to encode and just attach it to the message,
Mhm.
right? And then so I guess that encoded extra bit, you're saying you can adjust how much or how little is encoded to
Right.
increase or decrease the storage needs of the message. But if you do, so then I like to understand. So if I bring it down to only a small amount of it is encoded, then I
Mhm.
need more participants because I need to ensure that the redundancy is there. But if a large amount is encoded, then I can have less participants in the network.
Right. So it depends what type of redundancy scheme you are using. So if you are using encoding, you just need a small number of participants. If
Okay.
you are using replication, which means you duplicate or triplicate the data without any mathematical encoding, then you will need a large number um, of participants.
Mm, okay.
But yeah, exactly what you said is that you can tune exactly how much you want to produce as encoded data, in order to calculate how much, to know how much space extra you will need, and you can play with this parameter. So that's very convenient.
Nice. You realize like when I'm driving my kid around and he asks me how GPS works now. Now I get to sound like that dad. Like I know how all of this works, child. It's erasure coding. No.
I hope he doesn't get bored.
Okay. I did have a question. It was probably a little while back. I know there's different ways to sample. So are there different ways to sample data?
Right. So this goes into I mean, one of the questions is how much you need to sample and how often you do this. And for example, in the case of a storage system, if you apply randomness, which is the best way to do it, if you randomly decide who you're going to sample, then with just a very few number of samples you already know, you already have a very high degree of you know, assurance that the data is there if you got enough positive answers. So, for example, if you're a teacher in a school, and you have a class of 100 kids, right? And so you imagine, you say, okay, for tomorrow, so you give a homework for tomorrow, right? And so you say, okay, for the first half of the list, I want to check the homework of the first half of the list, and then next week I'm going to check the homework of the second half of the list, right? So what happens is that the next day, most likely, the first 50 kids in the class did their homework, and the last 50 kids in the class didn't do the homework, because why would they do it if they were told that they will not check it? And then for the next week, the opposite will happen, right? So you will have the first 50 they didn't do the homework, and the second 50 they did the homework, right? Now, if you tell them instead that instead of saying I'm gonna pick the first 50 and then the second 50, if you say I'm gonna pick 50 kids randomly, then they cannot play with this anymore, because then they don't know if you're going to be selected or not. So most likely you will have a large number of kids that actually do the homework, because they were afraid that they get picked, and then maybe a few ones will say like, I'm just going to play my chances, and then maybe some of them will not, right? But then, okay, let's imagine, so you pick a number of kids, and it turns out that the first week, every time you ask, like 50% of them did the homework and 50% of them did not do the homework. So you know that the average homework delivery is 50%. The next month, that decreases to, let's say, 25%. And let's imagine that gets improving. If you ask a certain number of times, let's say 30 homeworks, and every time you get all 30 homeworks done, then you know that the probability that there is 99.999999 probability that everybody is doing the homeworks, right? Because if you pick 30 random times random homeworks, and nobody and all of them were correct and all of them did the homework, then just basically that that we have a 99.99% probability that everybody is doing the homework. It's like throwing throwing a coin. You have 50% tail, 50% face. So if it's really hard that you throw the coin 30 times and you always get the correct answer, right? So the only way that happens is because that the system is producing these results, and so that's what we do. And with sublinear sampling, we try to minimize the number of questions that we have to ask, and still have a very, very high probability that the answer that we are getting is positive, which means that everybody in the network is actually storing the data that they have to store. But then, as you say, there are other types of sampling. Like, for example, is what type of answer you want to get for when you are requesting if the nodes have the data. One of the ways is saying, like, please send me the entire data, and then I verify it. Another way is you send me a proof that you have the data, and that in this case we're talking about a cryptographic proof. Now the problem is, if you want to store these proofs, on a dashboard or the internet for everybody to see that, to check that the nodes are still storing the data, then you can not really ask them to send you the entire data set as a proof that they still have it, right? In particular, if we are talking about the centralized system and Web3, most of the times you want to store the proofs into a blockchain. And storing data in a blockchain is extremely expensive, at least today. And so because of that, you cannot say, well, I'm going to store my proofs in the blockchain, because that would be just, prohibitively expensive. And then what you need to do is a way to create cryptographic proofs that are small enough and that you can post that in the blockchain. And then everybody can see that, oh yeah, my data is still there because 2 hours ago, the protocol asked this node and all of the 20 chapters that I stored are there. So my book is still safe, right? And that's how we do it. However, we have to ask these kind of questions. So these samplings is not done just once, because that's not enough. You need to do it at a certain frequency, right? You need to say, okay, I'm going to check, I don't know, 2 times per day or 4 times per day, to check if my data is there. And I assume that this is, that this is good enough for me. So every 6 hours I ask and I check. But then if you have to do this check for the entire system and you have a lot of data, then you are talking about storing a very, very large number of proofs. And that's where things become complicated. When you have to store a very, very large number of proofs, then you have to use other kind of techniques in order to see if you can compress those proofs all together into a small one that still includes all of the others, and you can use them. And there are techniques to do that. In particular, we call them succinct non-interactive arguments of knowledge, SNARKs for short. And it's just a mathematical tool that exists today to compress proofs into very, very, packed things that really packed a lot of proofs together into one small one. And that's what we use today for sampling at least in Codex. That's what we are planning to use. Yeah.
So one of the questions I have, you talked about the recursive compression scheme that you use, but one of the questions I have more is, how do you determine the frequency of repair that's necessary to maintain, I guess, a certain number of nines for the storage?
Right. So yeah, good point. So once you are, so we talk about erasure coding and enhancing or increasing the data. Then we talk about sampling. Now we talk about compressing those proofs into a small one. Now what happens if you have to act when a data is simply gone? So there is a node that for some reason burn out and they didn't provide the verification, the proof that they had to provide. You know that this node is gone. You ask several times in a row and there is no answer. So the data is gone. In this moment, you have to repair the data. And for that, you use the same encoding technique that you use to augment the data. So this same algorithm, you use it but backwards in order to regenerate the original data using the encoded data. Now, when you do this, you can do it every time that you see something missing, you can do it, right? But remember that in our example, we say, okay, I take my 20 chapters and then I create 10 more that are encoded data. And so now if I lose one chapter, I still have 9 others, which means I still can lose another 9 chapters and I will be still be able to recover my original data, right? So you can play with this, with these thresholds. You can say, okay, instead of repairing all the time, because repairing is not free.
You would incur a lot of proofs, and you would overwhelm wherever you're storing the proofs in terms of
right.
Yeah.
So that has a certain cost. And so instead of doing that, I can set a threshold saying, okay, maybe from this point, I will start reconstructing the missing data. And one of the interesting properties of this algorithm is that when you reconstruct, when you do the decoding, it doesn't matter how many data or how many chapters in the book are missing, because it will always regenerate the whole 20 original books, right? So if you had one chapter missing or you had 5 chapter missings, for the same calculation, you will get all of them. As far as you
There's a
didn't lose
caveat
more than,
though. There's a caveat there, right? In terms of like adversarial erasure,
yeah.
and excluding just enough data so that repair is not possible.
Mhm. Exactly. So you have to be careful with that, and so you have to make sure you don't get too close to the danger zone, and that you still have a certain buffer and some protection there. So we play with tuning these systems so that on one side we don't incur too much overhead by repairing everything that is perhaps not necessary all the time, but also we don't go to the other extreme where maybe we are getting too close to actually lose data, and that is catastrophic, because this is definitely the case that we want to avoid.
So how does this sampling kind of differ from some of the other data availability sampling that exists? I know Ethereum is doing some. Like, how's Codex is different and better?
Right. So yes, so we are working with the Ethereum Foundation on a project, on a research project together, and basically we are trying to help them, model the data availability sampling strategy for the next iteration of Ethereum. And the reason why it was a good project for Codex to participate on is because many of the strategies that we are using inside Codex are actually used in, or are planned to be used in Ethereum, right? For example, I was talking about the erasure coding. They're planning to use erasure coding. I was talking about sampling. They're using to use sampling. We're talking about data repair. They're using to, and this is all normative. This is not a coincidence, because the problematic is the same, in that what we want is to protect the data somehow, and to do this in a system that is decentralized, a peer-to-peer network, and that nodes go down from time to time, and other nodes are not nice and play bad. And so there is just a limited number of mathematical tools that can help us, and we all try to use those tools and the best ones for the task. So that's why this collaboration makes sense, because we are using the same tools. Now there are significant differences. For example, in the context of Ethereum, what we are working on is data availability. We want to make sure that the block that is going to be produced is available, but we don't need to guarantee that the block is available forever. We just want to make sure that the block at some point in time became available to the network, and that's it. In the context of Codex, the story is different, because in Codex, what we do is to guarantee data durability, which means you sign a contract, with a storage provider, and you say, I want you to store this data for the next 3 years, or whatever. And we need to make sure that the data is available for those next 3 years. So that means that, and we go back to the frequency of sampling that we were talking before. In the context of Codex, we need to keep testing that the data is available, every X amount of time. And that means that the frequency of sampling is completely different between Ethereum and Codex. In Codex, we have to think in long term. In Ethereum, we don't. So that's
Yeah,
that's
Ethereum,
already
they dump the data in 2 weeks. Like,
more exactly. Yeah,
yeah.
2 weeks or 3 weeks or whatever is the timeline is a different scope, and that is a significant difference. And that leads to another point, is that in Ethereum, you can actually do sampling on your own, and you say, okay, I'm going to check whether uh, the piece of this block is available, and I participate in sampling. And when I find that something is not available, I just raise this alarm to the network and I say, hey, I didn't find this piece of data, or I try to repair it if I want. There are different actions you can take. But that's you don't need to store these proofs into a blockchain, or at least not in the same way that you need to do it in Codex, and that leads to a difference in how much data that you need to store inside the blockchain, um, and regarding the proofs of the system. And also because in Codex we are looking at long-term and data durability, then we really need to make sure that the amount of space that we are using for proof storing is sufficiently small. Then we have to go and look into snarks and ways to compress these proofs into a very, very small space, which is what I was explaining before. And Ethereum, we don't necessarily need all that. There are parts of it that we need, but in a different way. There is data, as I say, there is no data durability in Ethereum. So, you don't have for a specific set of data, you don't need to provide proofs for 3 years. You need to provide proof for a very short time. And another thing that I think is different is that the way you encode the data is it can be there are many ways to do it, and then that is really goes into how you want to design your protocol, and there are many flavors. For example, in Ethereum we are using two-dimensional Reed-Solomon encoding. Two-dimensional means that you take your data set, you divide it into small blocks, and then you put those blocks into a little square, two-dimensional square. And then you take every line and you augment it with erasure coding. So you produce a longer line for every line. And then you do the same for every column. And then you just do the same for the extra columns and the extra lines. And so what happens is that you end up with a larger square that is kind of protected two-dimensionally. It's just a pattern to protect the data. In the case of Codex, we are not doing exactly that. We are also using Reed-Solomon encoding, but we are using somehow I think it's a one-dimensional way of Reed-Solomon encoding. We also have a two-dimensional structure, but it's not exactly the same as in the case of Ethereum. So that's different. So something else that we're also using, that we are planning to use for Ethereum, is KCG commitments. KCG commitments are basically just a way to demonstrate that the erasure coded data that you produce, so the encoded data that you produce, is actually correct and is part of this line that I'm encoding. Okay, and then I can just send you a piece of that data with the proof, the KCG proof, and then you have a very easy way to verify that the data that I'm sending you is not just garbage, because that could be a possible attack, right? I could say I'm going to encode the data, but I'm not really encoding anything. I'm just producing garbage information, and then I just spread this information, and then everybody believes that everything is fine and well. But when you want to reconstruct, you cannot, because the data that was dispersed at the very beginning was actually not really useful. And so the KCG commitments help you to guarantee that what you are spreading on the network is actually real encoded data that will allow you to reconstruct in case of failures.
So it sounds like a technical undertaking, a huge technical undertaking. What about for the end user and maybe businesses, if they decide to participate in this network? How do they do so with protections? Like, how is their privacy protected and the other users' privacy protected? I guess what I'm saying is, if I'm electing to use my hard drive to store stuff, uh, you know, how do I know somebody's not putting some bad stuff on my hard drive, and how am I protected? Like I don't want to. Like that's their data, not mine. I know it's stored on my system, but it's not my stuff. You know what I mean?
You're
How do
Right.
talking about
you?
wanting some sort of plausible deniability for data that is illegal.
Yeah, like if I go to a storage unit, I got to sign a bunch of papers that say I'm not storing illegal stuff in their storage unit,
Mhm.
right? And that's their protection. Because what if I am? And then the police bust into the storage unit, and then you know what I mean? Like, what are the protections for the end
Right.
users?
Right. So this is of course a very difficult topic and a very important one
Hmm.
because exactly if you want to participate in this network and you want to help the system offering your disk that you are not using, you want to have those protections. One way to protect the user would be, for example, to enforce encryption on all data sets. Now we are not sure this is the way we will go with Codex. There are some systems that implement that, um, but this will be a way to say, okay, the data that I receive is encoded, is encrypted, and I don't have any way to decrypt it. I don't have the keys, so I'm just storing this. That is already an extra protection on top of the other encoding system that we are implementing in Codex, because when somebody uploads a data set, you don't even get to know what type of file it is, because you don't get the file, you just get the piece of the file, right?
Hmm.
You just get a block of data. This block of data is also not necessarily a contiguous part of the file. It's probably it's the composition of many small blocks, and perhaps many of those blocks are actually encoded blocks, not only the original data. And so what happens is that the data that you are getting is really a scramble of many small blocks after the encoding was produced, and you are getting original block as well as encoded blocks, and you're getting all this packet together. So in a sense, the data that you are already receiving is very, very hard to understand in a possible way, and to make any sense of it. But if you wanted, yeah, you could apply encryption on top of it, and say, well, anyway, even if I manage to remake all the order in between these small blocks and everything, I will not be able to decrypt the content because I don't have the keys. So
Oh,
yeah.
okay. Sorry, I interrupted you, but the light bulb went off. So it's like, there's like a 5 million piece puzzle of like the sky, the hardest puzzle on the planet, right? Like here's a 5 million piece puzzle of blue, right? And
Exactly.
then on my computer, you're like, and here's 4 pieces. Don't know where I got them from.
Mm,
They could be border pieces or they could be in the
yes.
middle, but here's 3 of them. Good luck, right? There's
Right.
really no way for me to even know what the data is. So,
Exactly, and
okay,
remember that 1 million out of those 5 million pieces are actually not part of the original picture of the sky. Is other
it's another puzzle.
encoded. It's encoded sky.
Oh, okay. Well, there you go. I would go to court on those grounds. I would be like, you put that piece together, you put that puzzle together, judge. So, and then I'd
Right.
get sent to jail. But no, I'm kidding. I'm kidding.
Right. No,
um,
but it's true that it's important to pay attention to those details, because yeah, we want to make sure that we are doing things right.
okay. All right. Sorry, light bulb went off. I'll pass the rock to you, Jess.
Yeah, so just a recap of like all the different things we kind of talked about. So it sounds like Codex and the work that's being done with the EF, again, like you said, uses the same tools from the same toolbox in order to be more efficient with the amount of storage across the network. So rather than doing full replicas, like you said originally, you use erasure coding in order to reduce the number of people that need to hold parts of the entire data set. And then you also, on top of that, try to be conscious of bandwidth for the nodes. So rather than doing uh, very frequent repair, you have some sort of concept of laziness to this repair, so that you were saying that you're playing with the parameters such that the persistence of the file is guaranteed, and you're not crossing that threshold in terms of not requesting proofs often enough that the user actually ends up losing their file. So you want to make sure that they have their file forever or for as long as the contract is, but you're being conscious of the bandwidth
Right.
by regulating the frequency of the proofs down, the requesting of those proofs.
Right. Right.
And then in terms of the encoding scheme, I think you just covered that you're not doing the exact same data structure in terms of the 2D Reed-Solomon coding that is for the DAS, the EF stuff. Codex has its own data structure.
Right.
And then they're tackling completely different problems, like you mentioned. One is for the Ethereum Foundation. They're just trying to provide a way for validators to have access to data in order to replay or verify
A
state.
block. Mm-hmm.
Okay, a block.
A block
Okay.
and then a state, yes.
Okay. Versus Codex is trying to solve this problem of data durability, which is more persistence and like probabilistic retrievability of data.
Right. Exactly. And there is also another difference that I just remember now and I didn't mention, and is the size of the data. In Codex, for example, we want to offer users the possibility to upload any data set, whether it's just a small file or whether it's just a huge backup of your all your pictures or whatever, or movies, or anything that is legal, of course, and that but any size of the data. In terms of Ethereum, you always have the same amount of data, because what we are trying to protect in the case of Ethereum is a block that is going to be produced, and we have very specific sizes for this block. It cannot be a huge block of 1 terabyte. That is just unthinkable. And it's usually not 1 kilobyte. I mean, that's not the numbers that we are talking about. So here we are, for example, in the current model, which doesn't mean that it's going to be like that at the end. It can change, but we are thinking something between 32 megabytes that after encoded can be in the order of 120 megabytes. And so now we have a very specific size of the data that we are planning to protect. Okay. In the case of Codex, it can be very small or it can be huge. But when it's huge, then that applies a certain burden on top of the system, because you might have to encode this huge amount of data very fast, and that has a certain number of implications. And so that's another difference between the two systems.
So what are some, I guess, open-ended points of research or continued work that we'll definitely have you on to discuss for Codex, like in the near future?
Right. So in the context of Codex, we're still working on the snarks, on what is the best way to implement very succinct small proofs and how to aggregate those proofs in a very efficient way. We already have a few models that tell us how much space is going to be consumed by those proofs, given a system of a certain a number of files and average file size and so on and so forth. So we already have some models that allow us to predict these kind of things, but we still miss a couple of inputs. For example, we are still not sure how fast we can encode a proof using snarks. And that's something that we need in order to put as an input in our models to say, okay, this is the amount of time that we're gonna spend encoding proofs or aggregating proofs in the system. And the more files you get, the more proofs you get, and the more times you will spend aggregating those. And that is important because then if you need many, then you can say, okay, then maybe we need a certain number of aggregators in the system. Aggregators will be a specific role in the system, and node that only cares about aggregating proofs. It's not storing any data, it's not promising any storage to long term, but it's just aggregating proofs in the network. So those kind of things, we're still not 100% sure. We're still working on those. and that's still part of the ongoing research in the team in the Codex team.
Awesome.
Cool.
Can we have you back to talk about like use cases?
Excuse me.
Can we have you back to talk about use cases?
Yeah, sure, of course. Sorry, I don't know. I lost some of the
All
connection.
good. All good. I thought you were just like, no, you can't.